Welcome back guys to another video in the ICND1 video series. In this video we'll be going over what the Ethernet protocol is and how it's used for local area network communication. Okay, so the Ethernet protocol defines how two devices in the same local area network are able to communicate with each other and share information with each other. So we know how we can connect devices together in a local area network. We connect them to a switch, either through a wired connection or through some sort of wireless connection. But wherever it is, devices will terminate back at a switch or multiple switches. With Ethernet, Ethernet defines a set of rules that devices can follow in order to actually move that data from one device to another device. Ethernet also defines the type of cabling we use to connect to our local area network and how that cabling can be used to actually transmit data. Ethernet was originally designed for hubs, which operated as a shared medium. So with a shared mediums use a sort of bus topology, a bus architecture, in that all devices connect to the same wire. And essentially only one device can use that wire for sending data at any single time, which meant that if multiple devices try to send data at the same time, it wouldn't work. They would try to send data, you try to all use the wire at the same time, and the data would collide and would become corrupted. And scrambled. So with a hub, multiple devices connect to a hub. They're all seen as part of the same collision domain, which meant that if more than one device tried to send at any given time, that data would collide and it would be dropped. So with a hub, only one device in a whole network is sent at one time. Same thing as with a bus topology. So with Ethernet, we had to overcome this problem of how we could avoid these collisions from happening and how a device could know when it could send data. So how could a device know if no other device is sending data, so then it can then use the wires, the cabling, to send data. So what I'm trying to say here is that how does the device know when the network is free to use and actually send the data that it needs to? Ethernet defined logic known as CSMA-CD, which defined how a device could know when it could send data and what devices do when a collision happens. So with CSMA-CD logic, it defines that before a device can send any data over the network, it has to first listen in on the wire. So it has to first listen in on the network and sense if any other device in a network is trying to send data. If that's all clear, then the device is able to put the data on the wire and actually transmit it. Now, if two devices try to send at the same time in a hub-based network, a collision occurs. The data becomes scrambled, that data is dropped, and both devices have to resend. Now with collision detection, Ethernet said that if a collision does occur, then drop that data because it's going to have errors now, and tell the devices to wait a random amount of time before they try to resend that data. So by waiting a random amount of time, it kind of ensures that devices resend the data, but now at different times. Now, when we moved to switches, we didn't have this issue. So even though we use switches now, devices that use Ethernet-based networks still use the CSMA-CD logic when they're trying to send data. So whenever a device connects to a switch, a device will still listen in to see if any other device in that collision domain is trying to send data. But with switches, because each port represents its own collision domain, there is no chance that a PCA will ever hear another PC trying to send data in that collision domain, because as you can see, there's a single cable running to a single device, and PCA is the only other device in that collision domain, which means that devices that connect to a switch can all send and receive data at the same time, which effectively eliminates the collisions from happening. Ethernet also performs error checking through what's called the FCS field. So Ethernet performs error checking in that it can check whether the frame has any errors during the transmission of that frame. The way it does that, if we have two devices that are going to send data and communicate with each other, we have device A and device B. Before device A even sends that data to device B, it's going to perform some sort of error checking on it. So it's going to get that data, run it through some sort of mathematical algorithm, which spits out a number. That number is stored in the FCS field of the packet. When we look at how Ethernet frames are structured, we're going to see where the FCS field is. But anyway, once that data is sent to PCB, PCB is going to run that data through the exact same algorithm that PCA used, and it's going to spit out a number. If that number is the same number that was originally on the that was originally stored in the FCS field on the Ethernet frame, that means that no error has occurred. If the number is different, that means that during transmission something went wrong, something in the data has changed, so the data has error, is not worth anything, so we're going to discard it, and we're going to ask PCA to resend that data. And the way Ethernet works is that data is encapsulated into frames. So what's a frame? So as a device moves down the TCP/IP model in order to be able to send that data and communicate with another device, we add more information to the data. We go through the process of encapsulation. So originally we have the original data, and at the moment there's no way that we're able to get the data from point A to point B. We have to add further information to it in order for that data to be moved from point A to point B. And so the way it works, we encapsulate that data, we add headers or trailers to that data so that we can add additional information on, and allowing us to successfully move that data from point A to point B. So in this case, we'd add what's called a TCP header. And as we add headers and trailers to our data, where it's essentially adding more information, and each stage of information adding is called something different. So what I mean is that when we encapsulate data with transport layer info, that's called a segment. So a segment is data which has been encapsulated, which a transport layer header has been added to that data. A packet is defined as data that has been encapsulated up to the IP, up to the network layer. So what that means is that not only has transport layer information been added to that data, but also IP information as well, allowing devices in different networks to be able to communicate. A frame is defined as data that has been encapsulated up until the data link layer. So what that means is that not only have we added transport layer information to the data, we've added IP information and data link information, allowing us to be able to communicate on a local area network. So normally packets are sent between devices in different networks, but then to get those devices, to get that data to the next device in line, we have to encapsulate that data further into a data link header and trailer, which is called a frame. So what I'm trying to say, at each stage of data encapsulation, that data is called something different. So Ethernet deals in frames, and we send and receive frames between different devices. Ethernet also supports different types of traffic, known as unicast, broadcast, and multicast. The unicast traffic is one-to-one traffic. Traffic is data sent from one device that's intended for only one other device. Broadcast traffic is traffic sent from one device, which is received by all devices on that network. Multicast is defined as one-to-many. So with multicast traffic, certain devices make a choice to join a particular multicast group. And so when one device in that multicast group wants to send traffic to all the other devices in that multicast group, it sends what's called a multicast frame. A multicast frame is sent from one device and is received by all other devices that are tuned in, that are part of that multicast group. Simple. So unicast one-to-one, broadcast one-to-all, multicast one-to-many, and those many have to be part of some sort of group that the sending device is also a part of. Auto negotiation we'll get into after we go through the different types of cabling supported by Ethernet. Okay, so this is the frame structure of this is a structure of an Ethernet frame. We have the preamble, which is 7 bytes, the SFD, destination, MAC and source MAC, the type, the pattern, the FCS. So the preamble lists a certain bit pattern which lets the destination device know whether this frame that is received is the last frame in the communications going on between these two devices, or whether it should expect another frame. So as an example, we have two devices communicating. This device is sending a frame to this device. The preamble lets example PCB know whether this is the last frame in this communication sequence, or whether it should expect another frame from PCA. The SFD, all the SFD does is tell the device that the next bit of data you're going to read represents the destination MAC address. So it represents who this packet is going to. So normally with a switch, it tells the switch, okay, what you're going to read now afterwards is going to be the destination MAC address, who this packet is, who this frame is going to be sent to. The destination MAC address defines who we're going to send the device to locally. So it defines who on this local network this frame should end up at. The source MAC address defines the sending device. So destination MAC address, the receiving device, source MAC address, the sending device. The type field identifies the type of protocol encapsulated in this frame. So whether at layer 3 this is a IP packet, an IP version 6 packet, an ICMP packet, or another type of network packet. The FCS is used to store a number which is used for check for errors. We've been through this in the previous slide, where to make sure no errors have occurred before the sending device actually sends that frame, it performs a mathematical algorithm. So runs that data through a mathematical algorithm, spits out a number. That number is added in the FCS field. So now when the receiving device receives the data, it runs the data through the same mathematical algorithm, and if it comes up with a different number than what was originally stored in the FCS field, it knows an error has occurred and that data is no good anymore. Okay, so with devices themselves actually connect to a Ethernet network via a wired connection using what's called a RJ45 jack. So RJ45 jack is a network card which allows us to connect Ethernet cables into our device, allowing us to use those wired connections, those wired cables, to send and receive data. Now with the Ethernet protocol, devices on a local area network use MAC addresses to communicate with one another. So the way it works is that devices would all connect to the local area network through wired connections or wireless connections. And it's the source and destination MAC address which is used in order for PCA to communicate and talk with PCB. MAC addresses are 12-digit hexadecimal addresses, A through F, 1 through 9, and are 48 bits in length. This is the format of a MAC address. And when each device is first manufactured, it's given a MAC address which is unique to that device, which means that no two devices in the world will have the same MAC address. And the MAC address just defines how we send data. So the MAC address is used by Ethernet to define who is sending the data and who should be the recipient of that data. And like I said before, devices can only send when another device in the same collision domain is sending. Now with switches, because each port represents its own collision domain, it means multiple devices can send, because only one device exists in that collision domain, which means that device has full control over that collision domain and can send at any time. So now let's talk about the cabling actually used by Ethernet. So as well as defining the rules that devices have to follow to send data, so example, how we can move data from point A to point B, how we can check for errors, how do we know when we can send data. Ethernet also defines the cabling which is used in Ethernet-based networks. So it defines the cable formatting, the cable structure, how many wires in the cable, and so on and so forth. So Ethernet, the most common type of Ethernet cable are unshielded twisted pairs. So all that is a bunch of wires twisted together, which are unshielded, which have no coating over them, so the wires exposed. The reason why the wires are twisted is to decrease interference from outside. Interference can cause the performance of the network to decrease. So by twisting the wires, it ensures that we have less interference from outside. And UTP cables are normally used to connect devices such as your printers, your servers, your laptops to the Ethernet switch. And so the more wires we have, the more twisted wires we have, the more bounds we have, and the faster we can send and receive data. And data is sent as electrical signals over the wire. The other type of cabling we have in Ethernet is known as fiber optic cable. Fiber optic cable is normally used for switch uplinks, so to connect our switches together, because we're going to have a lot of traffic running between our switches. So with a local area network just doesn't consist of one switch. It consists of multiple switches connected together, and we use fiber optic cable to connect these switches. Normally it's used to connect switches that are far away from each other, so let's say hundreds of meters or even kilometers away from each other. A fiber optic cable consists of glass fibers that actually carry light. Now that doesn't mean that we can send data at the speed of light. Due to how dense the glass is, data normally travels at 30% less than the speed of light. But the good thing about fiber optic is that the cables are longer and the cables are also faster as well. So there are two types of fiber optic cable: single mode and multi-mode. With single mode supports longer cables which can send data faster, send data much more faster. However, with single mode, the glass core of the cable is smaller, which means that less data can be put through at one time. Single mode cables are also much more expensive, and the light source used to send the data is laser. Multi-mode fibers, fiber optic cables, are shorter in length and support slower speeds. However, with a multi-mode cable, the glass core is bigger, which means that we can send more data through at one time. The good thing about multi-mode fiber optic cables is that they're cheaper than single mode, which means they're more affordable and normally used to connect devices which reside in a shorter distance away from each other. Devices that are far away from each other, that's where we would use fiber optic cable. So now let's talk about the different types of cabling known as straight through and crossover. Okay, so when two devices want to send data, the data is sent to the network interface card of a device in order to be transmitted. The data is put on a specific pin and sent out that specific pin. With cabling connects wires to the different pins in the network interface card, allowing us to connect two network interface cards together. So what you can think of it as is we have a network interface card over here, a network interface card over here. We have specific pins on this network interface cards which the data is put on, allowing the device to actually transmit the data and send it out. What we have is cabling which runs between the network interface cards. It could be a network interface card of a switch and a PC, or between two PCs. And those network interface those cables contain wires connecting the pins of one device to the pins of another device. Straight through cabling is used when we connect two devices together, the pins of two devices, the network interface cards of two devices that transmit and receive on different pin pairs. So, before we discuss, let me talk about pin pairs. Okay, so just so that you have a bit of background knowledge, PC servers, routers, printers, and APs send data on pins 1 and 2 of the network interface card and receive data on pin 3 and 6. Switches and hubs, on the other hand, send data on pin 3 and 6 of the network interface cards and receive data on pins 1 and 2. So if we go back to this example, PCs and routers and devices like that, data that they're going to send, they put on pins 1 and 2, and they send that data over those wires, out those pins and over those wires. Any data that they receive, they expect that data to be, they expect that any received data to come they expect any received data to come in on pin 3 and 6. With the straight through cable, we have a wire running, connecting pin 1 on one NIC to pin 1 on the other NIC, pin 2 on one NIC to pin 2 on the other NIC, and so on. So straight through cabling is used to connect our switches to our PCs. So as an example, we have a switch over here, PC over here, and a switch over here. The way it works is that when PC1 goes to send data, it puts the data on pin 1. That data is carried over the wire which connects pin 1 on the PC to pin 1 on the switch. Now pin 1 on the switch is used for receiving data, so the switch expects to receive data on pin 1. And the switch is going to send data to the PC over pin 3, over the wire that connects pin 3. And likewise, the PC expects to receive any data on pin 3. This is how we would use straight through cables for. Now, what if you want to connect two devices that send and receive on the same pin pairs? That's where a crossover cable comes in. So, just an example, if we connect two switches together and we try to use a straight through cable, it will cause a havoc. So what I mean is that this switch over here, switch A, and this switch over here, switch B. When switch A goes to send data, it's going to put that data on pin 3, send the data out pin 3 over the wire connecting pin 3 on switch A to pin 3 on switch B. When switch B receives that data, it's not going to know what to do with that data because it doesn't expect to receive data on pin 3. It's probably going to drop that data, or the data is going to collide with data it's trying to send out pin 3. So the way it works is that there are certain pins in the network interface card that a device expects to receive data on. If it receives data on another pin pair or on other pins of the network interface card, it doesn't know how to process that data. Likewise, there are certain pins that are used specifically just for sending data. So by using a crossover cable, we can run a wire from pin 1 to pin 3. So in this example, with a crossover cable, there'll actually be a wire within the cable itself connecting pin 1 on switch A's NIC to pin 3 on switch B's NIC, which means that when switch B tries to transmit to switch A, it will send it out pin 3, and the crossover cable is going to map pin 3 to pin 1. So now switch A receives the data on the pin it expects to receive data on. So crossover cable is used to connect two devices together that send and receive on the same pin pairs of the network interface card. And the more pin pairs we use, the faster we can send data. So a 1000 base T uses 4 pin pairs. So in this case, we use all eight pins to send and receive data. So pin 1 connects to pin 3, pin 2 to pin 6, pin 4 to pin 7, and pin 5 to pin 8. So just as a recap, when we want to actually send data, we put that data onto a specific pin and we send that data out those specific pin pairs. So in this case, pins 1 and 2 are used for sending data on a PC, and pin 3 and 6 are used for receiving data. So they work in pin pairs. So we put data on both these pins because it's a set of pairs, and we send data out those pins. So the way it works, the different types of cabling defines how we connect the pins of two devices together. So the pins of the NICs on switch A and the pins on the NICs of switch B. And so let's talk about cabling standards quickly. So Ethernet defines data transfer rate at 10 megabits per second. It's base T, which means it's UTP cabling, and it supports a maximum distance of 100 meters. Fast Ethernet supports data rates at 100 megabits per second. It can either come in UTP or fiber optic standards. So with UTP, it's only 100 meters long. With fiber optic standards, the cable can be 2000 meters long. Gigabit Ethernet supports data transfer rate at 1000 megabits per second. It can come in UTP format or fiber optic format. With UTP format, again, it's only limited to 100 meters. But with fiber optic format, it's limited to 500 meters or even 5,000 meters. That's how long the cable can be. With 10 gig Ethernet, we only support fiber optic standards. So we transfer data at 10 gigabits per second, which is 10,000 megabytes per second, 300 meters, 10 kilometers, or 40 kilometers. So we reached the end of this video, and we've seen how the Ethernet protocol can be used to send data. We discussed how Ethernet works. In the next video, we'll be discussing how IP works, and details about the IP protocol. I hope this has been informative for you, and I would like to thank you for viewing.